Great. Hey, thank you everyone for joining us. This is the Villanova team. It's me and Aaron Wemhoff, who's been with us from the beginning, and Calvin Lee, who joined us about 2 or 3 years ago. So I followed Andrea's instructions and prepared PowerPoint that I'm going to share with you guys. And we'll get started. Tell me when you can see the slides.
Yes.
Okay,
See the
thank you.
slides. They look good.
Thanks, Russ. Okay, so I didn't particularly like the format, but let's go through it. At Villanova, we've been working at single phase cooling, which we are de-emphasizing per your requests. That's project 2.1.1. We've been focusing mostly on two-phase cooling, direct to chip, which is the work that I supervise, and immersion cooling, which is the work Calvin Lee supervises. So we got a nice balance there, and two groups working on that. And then we have the data center environmental impact work, sustainability work that's led by Aaron Wemhoff. So I think you all know our team. You may not remember, but Jerry Jones retired and is no longer kind of part of the group. We miss him, but I know he's having a really good retirement already. So we do still see him, and I may get him involved in at least one project because he's a heck of a modeler, and we really miss that, that capability. Let's start with the project 2.1.1, which is a single phase work. There's a little bit of work left to be done, but one of the things is Ben Margaritondo finished. We were working on microchannels at the request of a group that involved Cool IT, ERG Aero, and most recently Fabric 8 Labs. About 4 years ago, Cool IT and ERG wrote a nice, proposal of work, and then followed up by providing us many samples of microchannels, foam, and most recently more complex gyroid type structures that we've been testing. So the microchannel work is 100% completed, and Ben Margaritondo graduated and went to work for JetCool. So we're not working on that anymore. We basically proved the CFD models work very well, and the even simpler models work very well for microchannels. On advanced surfaces, which is the work we're continuing, we finished the metal foam work in single phase. It's not of great interest, but we thought for consistency we'd finish it. And we are doing a little bit of work with gyroids to kind of, again, finish things up. My own interest is the following. I really am an admirer of the Cays in London database. I think those of you that work in heat transfer know the book Compact Heat Exchangers. And I've always been an admirer of the way they compiled all that data very consistently. So I have a personal interest in compiling data for heat exchanger surfaces for cold plates in a similar way. We do want to do some modeling on the single phase water on these complex porous structures, because that part is not easy. I'll show you what we're doing there. So we completed the microchannel studies. We're now working on these 3D printed gyroidal structures, which are exceedingly interesting, and a lot of interesting work to be done there. So we are now going to be measuring the effective thermal conductivity and other properties of these gyroids. And particular interest is how do we model these complex things, both in single phase and two phase. We'll probably work on it for about another year on the single phase. Would be the master's thesis of Shreyas Shankar. From the point of view of outcomes, we finished the microchannel models in CFD. We acquired some very sophisticated software called NTOP, which Fabricate uses in their fabrication, their modeling and fabrication. We rebuilt a thermal conductivity apparatus completely to make measurements of the effective thermal conductivity of these complex porous cold plate structures. So we are de-emphasizing the single phase work, but there are a few things we want to finish here. So I wanted to focus on the two phase cold plate work.
If I
Yeah, go ahead,
may,
please.
if in Dave Cody's way of looking at things, winning now, winning later. Winning now is a single phase. Uh, and there were some substantive increases in heat transfer coefficient and figuring out when you have problems with erosion and such. And that's what you are finishing up. The question of winning later, uh, at least my vantage point, the data center industry, particularly where it's liquid cooled to help the AI, uh, is they've almost totally adopted the pumped single phase.
Right.
So your question is the question is, what do you do to win later? A uh, you go to something like two phase or other, or one other one is when you I like the concept of compiling all this in a case in London kind of form, which would allow you to look at it and say, what's best? And do you see a way to increase the heat transfer coefficient an order of magnitude? Say an order of magnitude, and if you get 5 times more, that might be winning later.
Hmm.
So if you could add that to the end of just say a what if, uh, can we predict a structure that would substantively increase heat transfer coefficients in single phase?
That's that limits thing that we were just discussing.
Yes.
I've always been personally very interested in this because that's physics. And I thought many times, well, okay, how do we establish physical limits, right? How do we determine, well, how far can we push?
Yes.
And
One of
yeah,
my experience, if you have one answer or one potential answer, which is two phase, chances are it won't work. If you have two potential answers, they may both work, and at least one will work, which
right.
is why I would encourage you to, before you close the book on single phase, take a look at that.
Yeah. Well, so a couple of comments, Russ. One is erosion limits. Okay. Of course,
Yep.
this is really important. And as you look for these limits, one trajectory is you keep on pushing the flow. I'm not a big fan of that approach, but the reason is because the more flow you use, the less effective is your engineering solution. You should really
Mm-hmm.
be looking at a solution that uses the least flow, not the most flow, right? So I've been a big fan of this idea of effectiveness, cooling effectiveness, which basically is looking to maximize effectiveness by minimizing the flow. But if you are going to continue to push the flow, then erosion limits become really important. So I have thought about launching a project on erosion. And JetCool, one of our newest members, I had a long discussion with them about what kind of project they would like to see. And that is actually the project they would like to see, us working on is identifying erosion limits. And as you know, they have cold plates that are impingement cooled. So they're very different and they are very aggressive kind of geometries. Same
Mm-hmm.
as the micros cold plates, they're impingement cooled cold plates, which do push the limits, but they also push the erosion limits. So I don't know, we may want to think about doing an erosion limit study. That would be an important consideration. Here's the reason I think it's what you're saying is I agree with. You all know that once one phase infrastructure is in place, we ain't gonna move it very easily, right? It's going to stay in place. We want to keep it in place as long as possible because
Right.
because of the investment. So we need to continue to look at the single phase and how far can we push it. And there's many trajectories you can go. You can push the flow. You can make better surfaces. You can make larger cold plates. You can use Corey's on the line here. We just started a project on heat spreading. If you're going to do some of these things, you're going to have to spread the heat. And so we identified an area for, including potential advanced heat spreaders for cold plates, things like that.
Yeah.
So I guess the reason we were de-emphasizing the single phase is because we were doing fairly traditional work, right? Which
Right.
can be done now using CFD and can be done, there is no research there. We can model almost anything single phase with CFD. That's kind of what we wanted to de-emphasize, but maybe we don't want to de-emphasize some of these other directions that we want to take, like limits. Maybe what we ought to do is identify or focus on limits, right? How far can we push single phase?
Right. Sounds good. Thank you.
Okay, thanks. Great. I wanted to start this discussion by something that I wanted to, this is a two-phase discussion, two-phase cold plates. Okay, so this is not ES2 work. This work is actually motivated by our ARPA-E project, but it really motivates our ES2 work, okay? So we've been working on really large microchannel cold plates, sort of the frontier cold plates for really large GPUs. And we have been studying, this is now two-phase refrigerant R134A. We are now studying alternate refrigerants, but this is the R134 data. And what I wanted to show you is, you can read the stuff on the right that basically is our heat transfer coefficients and temperatures and how well we'll be able to predict them with correlations. Bottom line is the following. We can predict the heat transfer coefficients to no better than about plus or minus 40 to 50% with correlations. They're not very good. But we can predict the temperatures to better than, plus or minus 15%. And the reason is the graph on the left, the bar chart, it shows the contributions of the TIM, the copper base, and the fins at 3 different powers for one single flow rate. This is at 1.2 LPM for a pretty large cold plate. This is a 50 by 50 millimeter fin area, a large GPU type cold plate. Okay, with R134A, it's got a fin base thickness of 3 millimeters. Okay, what it shows, okay, so the red dotted line is kind of our current target of about 0.01 degrees C per watt to manage to handle, the kind of power is 3 kilowatts or higher for these GPUs, right? So you can see that if you look just at the fin resistance, just at the boiling refrigerants and fins, we're well below the 0.1 target, right? The reason we're above the 0.1 target is because of the TIM and the base, right? The extra resistance of the base and the TIM. So I guess this is the main thing I wanted to point out. Going into what do we continue to work on? Yeah, we want to continue to reduce the green as much as possible, right? The fin resistance, the boiling, convective heat transfer, but we also have to reduce the base thickness and the TIM resistance. So that is something I'll address on future projects, because I think this is what we've seen is we've only been working on the green part. We think we need to be working on these other parts as well. Okay, so our project is this 221, and I have quite a number of students working on this project, including a student at Binghamton, Farzaneh Hosseini. We've been working on microchannels where we've developed baseline data. We understand the physics, the limits. Another thing that we've shown you in our monthly calls, we've been developing these data-driven ML techniques for optimization. They seem to work pretty well. You can get experimental data. You can train your ML model to optimize. And Abulfazl Baluchian has shown how that can then be used for optimization. And it worked really well. Then we've been working with ERG and Fabric 8 and others on these porous media cold plates. We've been taking experimental data on foam. We pretty much finished that with the work of Deo Kisitu, and we're now focusing more on these 3D printed porous cold plates, which are being fabricated for us by Fabricate, one of our partners. The results are very promising. I'm very interested in the modeling part. How do you model two-phase flow through these very complex structures? That's a big challenge because we're now barely learning how to model two-phase CFD with simple channels. So doing two-phase CFD modeling in these complex 3D channels is very complicated. So we're going to continue working on these gyroid coplates. We're not going to start with a CFD, full CFD. We're going to continue working on more approximate two equation porous media models, which have already been shown to be successful in the foam. We'll see if it's successful for the gyroids. I see this as about a 2-year more project. What I wanted to show you is why I think this is worth continuing. So this is very recent data comparing everything we've tested so far: foams, sky fins, gyroids. This is the boiling curve for R134A. The bottom line is we kind of get a cluster of the sky fins and the metal foams, all about the same performance. But we recently tested these gyroids with 80% porosity, and you can see that's the black circles, and you can see that it well outperformed all of the other surfaces, which was pretty exciting to us. We redid the data. We redid 3 of these sets to just confirm that this was true, because I thought the metal foam was actually higher than the sky fins. It is slightly higher, but not significantly higher. But the gyroids, 80% porosity gyroids, are significantly higher than everything else. Higher heat transfer coefficients, basically. So that's why we're going to continue the gyroid work. So I'm going to hand this over now to, unless anybody has any questions right now, we can move on to the immersion cooling project with Dr. Lee. We can come back on discussion after the slides. Go ahead, Calvin.
All right, thank you, Al. Yeah, great discussion. So this project is really push the fundamental boundaries. So as you see the title, right, two-phase immersion cooling, evaluation of current technology and fundamental explorations leading to improve of performance and reliability. So based on this concept, we're pushing the physics. So we look at what's the physics we are working right now. So if we look at, let's say, immersion cooling, what's the difference between immersion cooling and, let's say, pool boiling, right? So you would say if you want to really push the fundamentals, push the physics, it has to be something similar to the pool boiling. Then what else the physics you could add on top of that to do your immersion cooling thing. So what we figured out is we have to have those boiling surface on top of the chips. We could do that directly, expose the chips to the let's say R134A, whatever the immersion cooling refrigerants. But the surface is, after the package, the surface is smooth and the surface itself won't have anything for heat transfer. So we propose the new physics has to be on the surface and the interactions between surface and the refrigerant. Al, if you could please advance one slide. Yeah. So this could directly support Al's work on the microchannel two-phase heat transfer as well. And I believe you all attended the talks from Binghamton and also Arlington. So they also worked on similar projects, but not exactly in this scope. So our scope is really to understand what is the new physics, what's the limitation of existing physics based on the pool boiling study. So what we did was we look at the critical heat flux. That's one figure of merit of boiling heat transfer or two-phase transfer, immersion two-phase heat transfer that we would like target at. So the physics of critical heat flux, the maximum heat it could handle before it jumps to fume boiling, which is a really bad low heat transfer coefficient two-phase heat transfer regime, right? So we think about okay, if we could just based on the the state of the art of the fundamental principles of critical heat flux for pool boiling, then we could add something on that, the new physics. So for critical heat flux of pool boiling, the current understanding is a blanket of vapor covering the heating surface, so separate the liquid from the heating surface, so there is no direct two-phase heat transfer on the heating surface. So in order to understand why it happened and how we could prevent that from happening, push the limit. So we needed to make sure we can maintain a layer of liquid directly on top of the heating surface. So absolutely, porous media, right? Porous media is the structure we have been using to maintain that liquid layer on top of a heating surface directly by the capillary force, right? Capillary pumping effect. So that's what we are working on. So Al, if you could advance to next. So here we go. So this is based on our understanding of the physics that porous media regarding to critical heat flux. So if we look at this layer of liquid inside, it's almost like okay, we want this layer to be there, and then the relationship between this layer and the critical heat flux, which is that a blanket of vapor, actually is the evaporation on top of this liquid layer. So we maintain this liquid layer sandwiched between the vapor and the heating surface, solid heating surface. So the relationship of heat transfer is evaporation on top of this liquid layer to the vapor, and on the other side, it's a liquid to solid contact through conduction. The heat would conduct it through. So this is how we look at cannot see the slide. I think it's shared. I can see it. I think
Yeah, it looked like they're being shared.
yeah. All right, so it's
Yes.
recorded as well. Yeah, it's also it will be uploaded to our SharePoint. So if you can bear with me, if we look at the porous structure, it's about the porous structure thickness and also the pore size, porosity and pore size, right? If we look at the top equation, this equation involves the capillary force, capillary pumping effect. It involves the permeability. It involves the flow resistance inside the porous media. It involves latent heat transfer on top. So it covers all aspects, the parameters of this physics process. And then if you look at the figure on your right hand, then you will see that we collected a lot of previous experimental studies about this capillary-driven evaporation study with the assistance of a layer of porous media. So you would see there is extremely high heat flux and extreme high heat transfer coefficient by Hanks. This group of authors, they did some kind of environmental parameter manipulation, including the pressure, including other things, environmental pressure, those kind of things. So they could push to a 400 watts per centimeter square with so 400 to 500 with 40 watts per centimeter square per K degree temperature, right? K, which is the absolute temperature unit. So it's extremely high, but it has achieved with extremely complex manipulations. We did we look at the way they did, and we think actually it's a method that we probably could adapt, but also we want to make sure we have a structure to targeting our own refrigerant, right? So you see they have a R245 and they have a patent so for their validations. But anyway, so we are using our own structures to meet the need of our own working fluid. So if you see this SP6, this work, so we kind of understand how we manipulate it. So experimentally, we reach 300 and reach 15. Of course, there are much more room to improve. Instead of a manipulator pressure, manipulator other things, right? Generate other dynamical process. We just use structures. Anyway, so if we look at the figure on your left hand side, you will see that this is based on our understanding of the physics, and we are trying to push where is the optimal combination if we just use a uniform thickness porous media, but we can control the pore size and porosity and interactions. So you will see that we have our SP1, SP6, SP9, those experimental results and the other experimental to define the range we would like to work, and then use these theoretical predictions to guide us where that optimal combination of pore structure features should be for us to achieve the limitation, the maximum outcome from the combinations between the structure and the working fluid. So I know it's an exciting stage we have achieved, but we still need to narrow down this range and also broaden this range with the guidance of our understanding. Yeah. So Al, if you could please advance. Oh, okay. So I seem like that's all about my. Okay. All right. Thank you. I think that's it.
All right. So I'll take over here. So next 5 minutes, I'll tell you about my project I'm working on. This is the primary project. So if I know some of you have been on the meetings, the mentor meetings for Project 421. We actually often go into other related internally funded sustainability projects as related to data centers. For example, I have some undergrad students looking at things like power grid disruptions due to the presence of AI facilities. We did a lot of work looking at waste heat recovery for hydrogen production, as well, looking at waste heat temperatures for a variety of cooling system types and so forth. So I encourage you to check that out or contact me if you have questions about it. But this is the lone ES2 funded project. It's Project 421, looking at environmental burden reduction through water and carbon recovery. This project is actually a two-site project. It's not only Villanova, but also UT Arlington. Essentially, the Villanova site, which I'll tell you about here, focuses on using waste heat for water recovery, and UTA focuses on using waste heat for carbon recovery. So I'm under the presumption that UTA included the carbon recovery stuff as part of their site overview. But you can see here that for the water recovery side, we really have two high-level objectives. So the one that was originally involved with this project was actually the objective 2, which is looking at what are different ways and how effective would it be to take waste heat from a data center and use that to reclaim water on site. But we also had another side project that had started up about a year ago that has morphed into its another corollary with this project, which looks at applying statistical analysis to a variety of data center cooling systems and geographic locations, and seeing how that would influence the environmental sustainability of the data centers or the environmental footprints of the data centers. So here are the two objectives here. So objective 1, which is that statistical analysis project, what we did is we took an existing paper that came out a couple of years ago where these researchers had applied statistical analysis to look at 10 cooling system configurations that are commonly seen in data centers. And so these are all air-cooled based configurations. And what they did is that for all the ASHRAE climate zones, they came up with PUE and WE calculations of ranges that would apply to them. What we're doing is we're taking those 10 configurations and we're breaking it down at a county level, because in past research through ES2, we've been able to come up with some environmental metrics that translate the PUE and on-site water consumption through the WUE into these more environmental specific metrics, which are the carbon usage effectiveness, the scope 1 and 2 water usage effectiveness, which is often called WE source by the green grid, and something we're calling the water scarcity usage effectiveness, which is the water consumption as related to water availability. So think of the water scarcity footprint over the IT load there. So we've made a lot of progress in that and making that translation of those original 10 cooling system configurations into county-specific values for each of those three environmental metrics here. Since then, one of the IAB members had also requested that we develop an 11th air cooling configuration because it's seen in hyperscale data centers quite frequently, which is a modification of one of the earlier configurations. Now, these earlier configurations used a Python statistical package that we tried to reproduce, but we had some struggles with it. We're not sure the documentation was very clear in how they did it. So we ended up doing something a little bit different, and we applied a Monte Carlo analysis to replicate one of their cooling system configurations that was the closest to the one that the IAB member had requested. And we're able to get good agreement. And so from that, we're able to modify that approach that we used to get an 11th configuration per their request. And now that we've been able to do that, we're now extending it to a liquid cooled system case and hopefully multiple liquid cooled systems cases. So we're going to apply the same approach that was used for that one system towards a variety of new systems of interest to the IAB. So as we're doing that, we also want to examine the variation of waste heat reuse for the system and use and location. So the idea here is now that we're able to model these systems and we're able to look at the different types of environmental metrics, we can also see how implementing waste heat recovery could impact the modification of the environmental footprints for given geographic locations as well. So we actually have a proposal external to Villanova, or external to ES2 rather, that was submitted and is now under review for doing this specific thing. But if that proposal doesn't get funded, we would still integrate as part of the work here with 421. The other thing we're looking at is that once we have that waste heat recovery, then we can see how the environmental footprints could be reduced. So we're looking at the viability of waste heat recovery, not only for based on the cooling system, the geographic location, but also the end use type. So in other words, the waste heat recovery temperature, but we're also looking at how that correspondingly reduces the environmental footprints. So the second objective is looking at, can we just use waste heat to recover water? And we've been able to do some preliminary results with that using our existing VTOS tool, which is a flow network modeling tool that we started developing back in ES2, way back at the beginning. It was actually called Project One back then when we started in 2012. And it's matured enough that we can use that tool to look at things like water reclamation effectiveness. And right now what we've done is we're coming up with ways to modify our systems to be more accurate using data from literature, going to modify VTOS and then apply it to get updates on those water reclamation effectiveness calculations. Once we have that, we'll apply it to different climate zones. So in the ASHRAE climate zones that we have representative locations, and we're going to use the TMY3 database to look at, for a given climate zone, what would be the overall annual water reclamation capability for each of our different types of cooling systems that we're modeling. And then once we do that, then the big question is that often in order to do the reclamation, we have to dump in an additional power, which affects the scope 2 water consumption. So how would, the question remains then is that even if we generate more water on site, we're using more water upstream. So how does that play a role? Is there a net positive effect in all of this? So that's the final part of this, along with looking at the potential end use of using water reclamation to store up water for periodic drought conditions. So we're going to look at what's out there in terms of data that can anticipate the duration of droughts in a given location. And perhaps that stored up water we can use with that waste heat recovery could help the data center overcome any sort of water shortages that would occur because of these periodic droughts. So that's what we have. Just very briefly, here are a couple of the systems we're looking at. The first one, I believe Microsoft had mentioned this, is a direct evaporative cooling and condensation approach. So the idea here, without getting into it, is you look at that case A, We're drawing air in outside through an evaporative cooler, so it's humidified, the temperature's brought down. That goes into the data center hall, upon which it goes through two coils. The first one is the higher temperature coil, which then which basically provides the heat into a micro evaporator as part of a dual heat pump absorption refrigeration system. The output of that absorption refrigeration system is the evaporator coil, which is the interacts with the air through coil number 2. And as a result, we're able to condense out some of the water. So all these are condensation based. Case B is, we'll call this a hybrid data center, where some of the equipment inside the data center is liquid cooled and some is air cooled. And you can see here that the liquid cooled ITE feed into the micro evaporator. And essentially what happens is that you have the output of the cooling tower, that humid air plume that interacts with a coil that's connected to the evaporator. And so again, we have condensation based water removal. All right, next slide, please. And then this is from the first objective. So actually the objectives were swapped here, but that's okay. The minimal WSUE, which is that water scarcity footprint over IT load. We looked at a variety of different systems and we're able to come up with, for each county in the contiguous US, which type of system would give you the minimum water scarcity usage effectiveness. And you can see that it really depends on geographic location. Whereas in this case here out east, it looks like case 11 is your optimal system, whereas out west, more like case 1. And you can see some schematics as to what each of these entail. Very briefly, case 1, you can see has adiabatic cooling along with airside economization with a cooling tower and a crawl unit. And then case 11 uses an air-cooled chiller along with economization. So I think that's all I have for my slides.
Say, Aaron, something just sort of roared into my head. Do you feel this work gets updated with higher temperatures that we might see with single phase direct to chip? It feels like maybe some of the parameters might change. I'd never thought about it and I've never said it out loud. So this is half thought through, but I just wanted to get it into your mind.
Yes, so it actually would impact it in two ways. One is when we model liquid cooling systems, we would have that would affect the ranges of PUE and WUE. Then that in turn would affect some of the environmental footprints. But also that's the key part of looking at for different locations what the waste heat recovery potential could be. So obviously with the higher waste heat temperatures, you can then look at more effective ways of reusing the waste heat, which then correspondingly reduce the environmental footprints.
Yeah, that's kind of where I was going in my thinking. Okay, if it was more rigorous, it might help people make decisions is all I was thinking. So good, thanks.
Yep. Well, actually, one of the things I failed to mention is one of the goals here is to come up with some online tools that can be used by the IB members to play with, these little online calculators that the members can play with to determine things like the effectiveness of water reclamation.
Let me move on here. Thanks, Aaron. Let me quickly finish up these slides and then we can open it up for further discussion. So we had a good year. We graduated quite a number of students actually. So you may remember Carol Caceres worked for many years on transient heat exchangers. He completed his work, got his degree. He's writing a couple of papers now. He went to work at IBM Poughkeepsie. You all remember Deo. Deo also graduated in December. He finished the work on two-phase heat transfer in foams, which turned out to be a really great project. He went to work at Dell. Ben Margaritondo was working on the Cool IT sponsored work on the single-phase microchannels. He went to work for JetCool, one of our members that joined last year. And Abul Fazl Baluchian just graduated. He's looking for a position right now in case he got a master's degree. He was a student working on the machine learning optimization work on the microchannel coplates. I don't think Alex graduated last year, but nonetheless, he was a recent graduate. He went to work for Vertiv And then Aaron's got a couple of students, undergrads, who also received their degree, and Megan Ward is continuing into the master's program. So it was a good year for graduates. One thing I'd like to see more is that more of our graduates go to some of our ES2 member companies. And that, I've said that before, and I just think it's a question of us alerting our members of potentially graduating students, like the student Abul Fazl, who's currently looking for a position. A couple of projects that enhance our ES2 work. The biggest is this big ARPA-E cooler chips project that we're a part of. The project that Villanova is a part of is the OmniCool project with NVIDIA, Vertiv, and Boyd and Binghamton University. It's related to green refrigerant compact hybrid systems, direct to chip two-phase plus single-phase immersion. We're doing extensive studies at all partner companies with the objective of demonstrating this hybrid cooling system. We recently convinced ARPA-E to allow us to make even more aggressive targets. So we're going to be actually demonstrating it at a 1 megawatt rack scale rather than the now obsolete, 120 kilowatt rack scale. So we sort of self-motivated ourselves at the, with the leadership of NVIDIA and Vertiv and others to try to hit even more aggressive targets. So at Villanova, we're doing a lot of expensive experimental characterization of two-phase cooling systems, cold plate to server to rack. A lot of this work is leading to open publications. And another thing that I want to bring to your attention is more recent work on digital twin development, where we are now working on two-phase CFD development as well as full system modeling using commercial flow network modeling tools. The idea being to simulate cold plate all the way to cooling tower using very, very large flow network models. One thing of note on this is we are working very closely directly with vendors like ANSYS, for example, who are very interested in the development of their tools. And so we're working directly with them on using their tools and basically getting their extensive input on changing their tools to make them, even more powerful for this kind of modeling. A lot of papers this year. Most of them that I'm showing here are all ES2 related work. Sometimes it's difficult to, draw a line between what was funded by ES2 and what was funded by ARPA-E or other funds, but as much as possible, I try to keep track of what was actually funded by ES2. So everything that I'm showing here was direct ES2 related research. So finally, some final thoughts on new projects. On the two-phase direct to chip, limits, we already talked about limits and how important limits are. An example is a lot of the work we've done so far is on 3D printed cold plates. In parallel flow, what we'd like to do is look at more aggressive jet impingement. I mentioned this earlier. We're already working on this. One thing to note here is the configuration of the flow has to be manipulated. So in this case, the flow would come in from the top and go out the sides. We're learning how to use 3D printing on these flow management objects in order to mount them on cold plates, and it's working extremely well. This was the project that was done by 3 very bright undergraduate interns this summer. Project number 2, for trying to reduce the thermal resistance of cold plates, there's a couple of other things that we can do. We can use larger cold plates. Larger cold plates will have lower resistance. In order to use them, we're going to have to use heat spreading. So we recently have started working with Thermovant, one of our latest members, on the possibility of using oscillating heat pipes as heat spreaders on the base of the cold plate. Interesting project. Thermovant has some very interesting technology. And so that is one way. The other way is possibly using vapor chambers. Vapor chambers are like heat pipes with wicks, but what I think would be interesting is vapor chambers with 3D printed wicking structures. I haven't really mentioned this much with our 3D printing partners, but I think this would be a interesting project. So in other words, use larger coplates to reduce your resistance, okay? The other thing that I mentioned to you was the need to reduce the base plate and the TIM resistance. So I had an idea that the idea was spurred by a comment made by Russ Tipton, okay? If you're trying to develop a coplate that has a lower base thickness, smaller base thickness, then you have to kind of optimize that coplate, both thermally and structurally. You have to make a coplate that structurally can withstand high pressures. The way we're doing it now is not going to work. We cannot thin the base plate on a skived fin coplate. So we need to move away from skived fin coplates, which what I would propose is using 3D printed structures or things like foams or other kinds of structures that would be then that would be adhered to the base plate and to the lid using different methods like methods that would be structurally sound. And then do a thermal structural optimization, which would optimize the structure not only for performance thermally, but also for structural performance. The last project that I would propose is given what we're doing right now with very large system modeling, two-phase modeling, chip to cooling tower, I wonder if we could take a piece of that and make it an ES2 project. And I'd like to discuss that further with you industry partners to see whether or not this might be something interesting, and if you might propose maybe some directions for this full system modeling. Under the two-phase immersion cooling, Dr. Lee's project, he initiated a project last spring, this spring, on the surface coating and the pore structures. He talked about that. The other thing is we're thinking of moving into a full system immersion cooling studies. We recently acquired at least one tank with the possibility of acquiring another commercial two-phase immersion tank, where we could study things like jet impingement and other, really aggressive enhancements to immersion cooling two-phase. So those are some of the projects that we wanted to bring to your attention. And I don't know whether you have any comment now, but that's our last slide. And I wanted to just open the floor for discussion and your input about the three major areas we're working on: direct to chip two-phase, single phase, two-phase immersion cooling, and then the water utilization and the sort of system modeling that Wim Hof is doing. So let me stop there and ask for you to comment.
One comment, Al, I really like that you're starting to look more closely at modeling in terms of digital twin. I know we've been working for a long time on compact models that can help, like we said earlier, understand the physics and the limitations of things. But if we make this more for the masses and have digital twins, I think our work would be realized and the value would be emphasized, I guess. So that feels like a great series of projects, and also interdisciplinary projects could emerge from that. So that there's something there.
Just one comment on the full system modeling. I think it's very interesting. I have one student working on a full system modeling, mostly for waste heat recovery, looking at the possibilities for waste heat recovery from different types of systems. But what I see in the landscape is really interesting these days, right? Because as we start looking at 1 megawatt data centers and possible on-site power generation, then you have all these different issues and questions and opportunities related to what can you do with waste heat from the on-site power? What can you do from the waste heat from the data center? If we're going to definitely see two-phase system implementation in the future, I think it's really important. Well, Vertiv would know as well as anyone how important it would be to understand the entire system, right? Not just the coplates, but the entire system. That's kind of why I think possibly carving out some kind of a full system two-phase modeling project might be a really interesting ES2 expansion of scope, basically. But for that, we really would like to work with some of you partners to help identify, well, what questions are we trying to answer, right? What are some of the things that could be done using this digital twin effort?
That's great. Thank you. You caused me to have one other thought, like you always do, is there's a piece of all of our work, even as a manufacturer, and we're designing new systems where we collect data. And you wouldn't necessarily give that data out publicly, but you might use it to, rather than a compact model, create, what should I call it? Create a body of synthetic data that could be used by other AIs and leveraged to ensure normal operation. Because during the benchtop testing and the evaluation and all the V&V we do, we know what normal and not normal looks like. And we could create it's difficult to have one AI train another, but if you have a large amount of synthetic data, you could allow that other AI to learn from that data. So completely off the rails now. So I'm going to stop talking.
That's not off the rails at all. I think I'm still talking, right? I mean, this is the larger question, in my opinion, Greg. How do private companies share data in a way that doesn't compromise their IP so that others can use their data or models in a large system simulator, right? This is a question we've been asking recently. And we started out with simple things like, how do we acquire data or models from a plate heat exchanger company and put it into our large system model? How do we get that data in a way that protects their IP, but allows us to use their model? So you talk about synthetic data. One way to hide your model, if you will, is to simply provide synthetic data, right? Which can be used to train an AI. That's an interesting way to allow others to use, your product information, right? I like that idea. It's kind of an interesting idea, especially recently. For example, we used data to train an AI model to optimize a cold plate. And it was experimental data, but we could use synthetic data. We could use simulation data to do the same thing. Well, those are good thoughts, but that's the larger question that I've been asking recently is how do we get data or models to use in a large system simulator so that we don't always have to develop our own models?
Maybe this would be a good topic for our IAB meeting in October to really talk about digital twinning and using data and
maybe establish standards. Maybe this would be an interesting opportunity to establish a model that could be, we could, talk about it publicly. And, this is what we've done with some of our partner companies. We developed this large system simulation with the contributions of models or data from end partner companies who have products like CDUs or cold plates or pumps in this model. And we needed to have that data in the model in order to be able to do this system simulation, right? This would be an interesting thing to do.
I wonder if there's going to be these kinds of discussions at Open Compute. I haven't looked at the agenda and there's not, I don't know if there's that detail available yet of the actual presentations, but I suspect there should be some discussion like this
Well,
at
given
Open Compute.
given that, one of their roles is to kind of establish standards, or at least, to establish standards and things like
Right.
that. Maybe this would be an interesting thing for discussion, is standards for modeling.
Yeah, I believe that the OCP administrative staff is going to be putting out a schedule here pretty soon, and maybe this week.
Cool. And speaking of Who here is planning to be there and is going to be at the IAB meeting and staying at the Hyatt place? Who hasn't responded to me yet? Greg, will you be staying at the Hyatt place? And I assume you'll be coming to our IAB meeting?
Yes and yes.
Yeah.
These days, Vertiv is like a squirrel that has his jaws so filled with nuts, and then he finds one more nut to pack in there. So it's kind of our time. Yes, thank you. And thank you for the reminder.
Okay. Anyone else? Corey, Ariel, are you planning to be at the IAB meeting? Ian?
Yeah, I'll be at the IAB meeting. I think Arad responded for our
Oh,
team
that's
as
right.
well.
He did. He did. Yes, I do have you down. Thank you, Ariel. Corey,
Yes,
Ian, will you be
sorry,
there?
I forgot to respond. I'll be there. I'm not quite sure yet if I'll, because I live locally up in San Francisco, so
Oh.
I may just commute.
Okay. Okay. All right. Sounds great.
Andrea,
Yeah.
so what it's worth, I plan on attending, but it all depends on family situation,
Yeah.
kid coverage.
Okay. Hope you can make it, Aaron.
I had a comment, this may impact, the project was 4.1, I think. I stay fairly close to, sales guys, technical sales guys. And what I hear, or what they hear, is that the hyperscalers, Microsoft and company, TCS temperature is 25 to 30 C. And this is for their new AI facilities. I think if NVIDIA tends to be the outlier, they're pushing about 40 C for TCS. But of not everybody pays attention to NVIDIA. It's like, I'll buy your GPUs and I'll go away. I'll take care of my own use of them. So if a 25 to 30 C TCS temperature has real significant impact on what do you do with that heat?
Yeah, I know, Russ, we had talked about that in terms of using the waste heat instead of for water reclamation with that project 421, but also cooling low temperature ITE equipment. And that I've done some analysis, and one of the things on my list is to collaborate with you on a paper on the topic.
Yeah.
Because I think it is an interest, and it was your idea to begin with, and I think it's an interesting thing to put out there. So yeah,
Yes.
well, I look forward to doing that with you.
Okay, cool. And the modeling of two-phase systems, chip to chiller. I don't know, for whatever reason, if it's single phase, the system, you're going to have tens, hundreds, thousands, tens of thousands of cold plates with one pump. So this incredibly challenging plumbing system, but it's just a plumbing system. You know, and so then you say, well, how do I make sure I get flow to every place it needs to be at the right amount? Single phase is pretty straightforward. Two phase is a whole lot different because your load could go from 0 to 100%. And the particularly in a cold plate, the pressure differential due to flow varies with not only the flow rate, but it varies with the heat load. How do you model that? And how do you make sure that every cold plate gets the amount of refrigerant it needs? So yes, it is time to do those kinds of models. Know that there's some real phenomenal challenges to them.
Yeah. So Russ, you know Mehdi Merabi, one of my PhD students.
Yes.
So we're going to do a full flow network model of a full rack.
Yep.
With controls. So I think one of the keys, if we're going to do these kind of models, we have to be able to do transient models, and we also have to be able to put controls as part of the model. And I mean, it is huge,
Yep.
but I believe these are research topics, right? That's what I think we should be contributing here. What's the value we can add, as a center? And I think in the two-phase modeling, how do you handle unsteady systems with all of these unsteady components, like you say, unsteady heat flow that require modulation, maybe of valves, in order to assure, balancing of flow and so forth. Yeah, they are very complex.
Yeah.
But I think it might be a worthy thing for ES2 to try to contribute to. So I made the decision to allow one of my students to call that a PhD dissertation. And I hesitated for a long time that flow network modeling was sufficiently, shall we say, academic to make it a PhD topic, but I changed my mind because two-phase flow network models are extremely complex, like you say, and it's full of challenges. So here's my question back to you then. Do I have it right? What value could we add as researchers to this area? Because I know for a fact that, for example, within your company, you have people working on things like this. What value could we add, that's not already being worked on? That would be a question for you all to help us navigate, right? What is it that's really, really hard that you're not quite on top of yet? Well, we might be able to help.
Yeah. One of the challenges, junction temperatures, maximum junction or design junction temperatures tend like 85 C. And we say, oh, the TCS temperature is 25 to 30 C. What are you doing with that delta T? And you mentioned controls. I think controls are very, very critical. The IT load can go from 0 to 100% in milliseconds. The control of the flow system, mechanical valves and such, 1 to 2 minute is 0 to 100%. So now we have a couple orders of magnitude difference in time scales of response time. And I'm not sure anybody has, I don't know if you'd ever get anybody to admit it, but my guess is that when you go 0 to 100% on the IT load, the cooling system doesn't respond quickly enough, so you have overshoot. And I would think I'm thinking there's a significant chunk of that delta T between 85 and 30 C as is overshoot.
Yeah.
And so how do you minimize overshoot? That's the control strategy. And how do you do that when you have several orders of magnitude difference in the response times? And then how do you do that with typical lifetimes of mechanical systems, like 350,000 cycles? So, oh, okay. So now if I get the control fast enough somehow, I have about a 2-month life. on the mechanical system. That's not good. Those are, some of it's just, what university can contribute is with that set of constraints, what kind of solution, what solutions could be available, could be proposed. And, and then, yeah, the not so deep academic portion of that is, show that maybe it is highly academic, show that whatever proposal you come up with can actually work.
So that's exactly the kind of input I think we really need to make this a project. I really can, well, first of all, do we agree that this is an area we should be working with? I think it is an important area. I think we focus too much on, sort of chip level, and I have come to realize over the last 2 or 3 years that it's just the beginning. The overall system is so complex for two-phase, just everything you're saying.
Yeah.
So, and I'm thinking we really need to learn how to simulate. The other thing is, as you know very well, constructing the laboratory test bed to test, models and such like that is really difficult and expensive. So there are not going to be very many places where we're going to be able to get good data, right, in order to test these models. So this is going to require some close collaboration, right, with
Yep.
with partners, like you all, right?
Yes.
Because you might be the only place that actually has a pilot scale setup, right, where we can
Yes.
actually get some data, where we can validate these kinds of models. You all have seen the labs we have at our 3 universities. We have some capability, some very good capability, and it might continue to increase. But I happen to think that eventually, we're going to need industry data in order to validate models, right?
Yeah.
Data from industry labs, because I doubt that many universities will have the scale of data that we're going to need, right? So those are just
Yes.
comments. The other thing I really like about this area is it is multidisciplinary. It's going to require some control specialists, to work with us. So it's another
Yes.
area where I think an NSF sponsored kind of a project would be really worthwhile.
Yes. Multidisciplinary. I could tell you that Vertiv, when we 5, 6 years ago, we said, yeah, this we need to get back into liquid cooling. Because Vertiv did that a couple decades ago, and the industry wasn't close to being ready. But you don't get too far into it, you realize that traditional org structure that works really well for air-cooled data center, the walls are in the wrong place, the silo walls are in the wrong place for liquid cooling.
Yeah.
And so yes, recognizing the multidisciplinary part of it, Vertiv is trying to deal with that. We are dealing with it. And university, you need to deal with that also.
Yeah, that's the truth. We're not well equipped to do true multidisciplinary work. Universities are very siloed, but at
Yeah.
least here we're talking about sub-disciplines within, say, one major discipline, which is mechanical engineering, right?
Yes.
Maybe a little bit of, computer science and electrical engineering.
Yeah, there have been some ES2 projects, I think in Binghamton, that were saying, oh, it's when you say, well, how do you, with zombie servers, how do you get rid of their energy use? Well, turn them off. That's easy. how do you turn them on in time? And so it was, well, can we predict the demand for server to process information so far enough ahead that we can turn them back on? So there are already ES2 projects that have looked at kind of the control stuff.
Right. And maybe we amp that up, or maybe we continue that with our Binghamton colleagues.
Yeah.
And make this into kind of a big digital twin effort,
Yes.
right?
Yes, Dr. Gose, I think.
Yeah, of course. Sure.
Yep.
Cannot. Yep.
Yeah, cannot.
Absolutely. Yeah. I know we're over time, but it's certainly worth it for us. Any other comments or things we missed?
I think that's, I've given
That's
you
a
enough
lot.
to think about.
Oh, you did.
Yeah.
You certainly did. Yeah. On the thermal structural coplate work that I mentioned, Russ, I need to
Yes,
talk with you offline about that.
sure.
Okay.
Yep.
Corey, Greg, Ariel, does anyone else have any other comments?
I will say that I think on the Honeywell side, we'd also definitely be interested in seeing that study of the full stack up of thermal resistance on the cold plate. That'd be really interesting work. And the
Great.
thermal structure optimization.
Great, that's awesome. I say again that the inspiration for that has come from many different sources, but the one that stuck with me, of course, was an offhand comment made by Russ. Okay, and you may or may not remember making this comment to me, but it really made me think, really made me think. That's why I need to speak with you offline.
Yes.
Okay.
Yeah.
Andrea, I think we're done, and I really appreciate the opportunity. I wish there were more people on board, but you know, we just need a few big thinkers to make us think. So we got those people on board. So, you know,
Maybe
we're
if
good.
we send out you know, an encapsulation of this to the IAB members and encourage them to attend the meeting in October where we can discuss more of this, it might motivate people to show up
Right.
to that meeting.
Okay.
We can have more of an in-person discussion.
Yeah. Just one comment maybe before closing here. I think, again, to our members, is I think sometimes a lot of our members glaze over fairly quickly because we get into details fairly quickly. And I would encourage us, as say the researchers, to keep in mind to first talk about the global ideas, the big ideas that are motivating the study. Maybe like kind of like what we did today before digging into the details. First, remind everybody why we're doing this, what's motivating this. Like the reason I threw up the slide with the bar charts that I showed you was because that's kind of what's motivating almost everything we're doing on the cold plates. This is what we've learned, and now it shapes kind of like other things that we know or we need to work on. If we could do that kind of thing most of the time, we talk, especially in our IAB meetings, before going into details, speak really, really clearly about why. Why are we doing this? What is the motive other than scientific curiosity? What is the reason we're working on this? Right? We need to justify it.
I think the information age is at an inflection point. The ARPA-E is a direct air conversion thing that you and I attended, and the Lawrence Berkeley report that shows that electrical power usage by data centers in the US right now is about 4%. And they were looking out to 2028. That's not far away.
Yeah, it'll go to 11%.
It was between 6 and 12%.
Yep.
And where's that come from? And it's driven, that increase is driven almost 100% by AI.
Yeah.
And And that's why we're doing this. Where do you, one is, how do you get that stuff? How do you get cooling and power to a megawatt rack? And then beyond that is, can we make it more efficient?
Yeah.
And how? That's not just an academic curiosity. This is stuff that is, I mean, it's coming at us like a freight train.
Yeah. So I mean, I cannot tell you, but this week I'm participating in 3 different events that are not even technical. I've been asked to comment so many times by newspapers, by all different kinds of groups that want to understand what's going on, right? Because there is, I wouldn't call it fear, but like you said freight train. That's what people are seeing. This is coming at you like a freight train, right?
Yep.
And when they realize the magnitude of it, for example, I commented to a Delaware newspaper reporter recently because she was reporting on a 1.2 gigawatt data center that had been approved for the state of Delaware. She asked me, well, what does that mean? And I told her, well, that'll power about 1 million homes, right? In Delaware, average size homes in Delaware. So you can kind of write that to give people a perspective of what 1 gigawatt data center means. It'll supply the power, for the city of Wilmington, right? And that's the equivalent amount of power, and that's what people are starting to see. So yeah, I would say that it is, an inflection point is absolutely what it is. Absolutely.
Yep.
Yeah. Well, that's why we need you guys on board, because like you're right in the middle of that inflection point, right? You might be driving the inflection point. I don't know, but you're certainly in the middle of it.
I don't know if we're driving or we're holding on for dear life.
Well, yeah, absolutely. We really appreciate working with you.
Yeah, I would say that just to kind of go along with what you said, Russ, the idea is how do you provide the resources to these mega facilities, these giga facilities, make them more efficient. But, and I guess I feel like one of the things that my role, going along with what you and Al said, is how do you do this without getting a public backlash? Because there is a growing resistance. And so that's what we're also trying to do here too. As like a third arm of that.
Yeah, I think that same ARPA-E, one of the presenters talked about, I think it was like 60-some billion dollars worth of data center applications were rejected. And some of it was not in my backyard, but I believe a majority of it is, we don't have the power. Where are you going to get the utility resources? And so, yeah, that's having a major impact on the planned growth of the AI revolution.
Yeah, well, that's why that reporter from Delaware wanted to talk with me, because there was a public backlash about that announcement. So yeah, it's becoming a big deal. The public perception of the industry, right? Yeah.
Yes, but the public's there with their cell phone in their hand.
Right, and requiring instant response for everything, right?
Yes,
absolutely, including their AI now, right? Including their ChatGPT, including their, everything.
Yes.
You can't have it both ways. Is that what we're saying?
Uh-huh.
Yeah.
Cool. Well, great discussion. Thank you.
Thank you all so much. Greg, Russ, Corey, Ariel, nice to meet you. I don't think we've met in person, but we love the Honeywell participation in everything we do. So thanks everyone. And Corey, welcome to the first big discussion like this. I told you that that's part of the reason for joining, is just to be part of discussions like this.
Absolutely. Thank you.
Yeah. All right. Thanks everyone.
Thank you.
Yes.
Thank you.
Bye-bye.
All the best.
Thanks.
Thank you.
Yeah.